The formula for calculating the neutral load in a three-phase 4-wire Y system is indeed related to, but not exactly the same as, the formula used for a three-phase 4-wire delta system with a high leg. The core concept revolves around understanding unbalanced loads and how current returns through the neutral conductor. Let's break down each system and the considerations for neutral load calculation. Firstly, consider a three-phase 4-wire Y system. In a balanced three-phase Y system, the neutral current is ideally zero because the phase currents cancel each other out. However, in reality, loads are rarely perfectly balanced. Therefore, a neutral current will exist. The neutral current in a three-phase 4-wire Y system is the vector sum of the unbalanced phase currents. To calculate the neutral current, you need to determine the current in each phase A, B, and C. If the loads are purely resistive, the neutral current is simply the arithmetic difference between the largest phase current and the sum of the other two. However, if the loads have reactive components, inductive or capacitive, the phase currents will have phase angles, and you must use vector addition to find the neutral current. A common simplified formula for estimating the maximum neutral current in a three-phase Y system involves considering the imbalance. If I, and I are the phase currents, the neutral current can be approximated by considering the worst-case scenario where one phase carries significantly more current than the others. This approximation often involves taking the square root of the sum of the squares of the phase currents. However, the most accurate method involves vector addition, which takes into account the phase angles between the currents. Secondly, let's consider a three-phase 4-wire delta system with a high leg, also known as a wild leg or stinger leg. This system is more complex than a Y system because it combines single-phase and three-phase power. The high leg is created by center tapping one of the delta windings, resulting in a voltage to ground that is higher than the other two phases. Typically, this high leg voltage is approximately 1.730 to the square root of 3 times the voltage from either of the other two phases to ground. The neutral load calculation in a three-phase 4-wire delta system with a high leg is significantly different from a Y system. The high leg introduces additional complexity because it is often used for single-phase loads, which directly contribute to neutral current. The formula you mentioned, the square root of a squared plus b squared plus c squared minus a plus b plus a plus c plus b plus c, doesn't directly represent the neutral current calculation for either system in its standard form. Instead, the neutral current calculation for delta system involves analyzing the single-phase loads connected to each phase and the high leg. Single-phase loads connected between phase A and neutral, phase B and neutral, and the high leg and neutral will create neutral current. To calculate the neutral current, you must determine the current flowing in each of these single-phase loads. Here are some important considerations for both systems. Firstly, the National Electrical Code, or NEC, provides guidelines for neutral conductor sizing and load calculations. Article 220.61 of the NEC addresses the optional method for calculating neutral load in a three-phase system. This section allows for a demand factor to be applied to the neutral load calculation, recognizing that not all loads will operate at their maximum simultaneously. Secondly, harmonic currents can significantly impact neutral current, particularly in systems with nonlinear loads such as electronic devices, variable frequency drives, and LED lighting. These nonlinear loads generate harmonic currents, which are multiples of the fundamental frequency, typically 60 Hz in the United States. Odd harmonics, such as the third, fifth, and seventh harmonics, are particularly problematic because they do not cancel out in the neutral conductor and can result in a significantly higher neutral current than expected based on the fundamental frequency load alone. To mitigate the effects of harmonic currents, you may need to use oversized neutral conductors or harmonic filters. Thirdly, load balancing is crucial in both Y and delta systems to minimize neutral current. Unevenly distributed loads across the phases will result in a high neutral current and increased losses. Balancing the loads as much as possible helps to reduce the neutral current and improve system efficiency. Let's delve a little deeper into the practical calculations. In a three-phase 4-wire Y system, consider a scenario where you have the following phase currents: I equals 20 amps, IB equals 15 amps, and IC equals 10 amps. If these are purely resistive loads, you can approximate the neutral current by finding the difference between the largest current and the sum of the other two. In this case, the neutral current would be approximately 20 amps minus 15 amps plus 10 amps, which equals negative 5 amps. However, this is a simplified approximation. A more accurate calculation would involve considering the phase angles of the currents if the loads are not purely resistive. You would need to use vector addition to find the true neutral current. Now consider a 3-phase 4-wire delta system with a high leg. Suppose you have a 120-volt single-phase load of 10 amps connected between phase A and neutral, another 120-volt single-phase load of 8 amps connected between phase B and neutral, and a 240-volt single-phase load of 5 amps connected between the high leg and neutral. The neutral current would be the sum of these currents, which is 10 amps plus 8 amps plus 5 amps, totaling 23 amps. The high leg voltage is typically around 208 volts relative to the neutral approximately 1.732 times 120 volts. Here are some additional factors to consider for accurate neutral load calculations. Firstly, voltage drop in the neutral conductor can be a significant issue, particularly in long runs. Excessive voltage drop can cause problems with equipment operation and can even create safety hazards. To minimize voltage drop, it's important to use appropriately sized neutral conductors and to keep the length of the neutral conductor as short as possible. Secondly, ground faults can also affect neutral current. A ground fault occurs when a phase conductor comes into contact with a grounded surface. This can cause a large current to flow through the grounding system and the neutral conductor. Ground fault protection devices such as ground fault circuit interrupters or GFCIs and ground fault relays are used to detect and interrupt ground faults to prevent electrical shock and equipment damage. Thirdly, the presence of other grounded conductors in the system can also influence neutral current. For example, if you have multiple neutral conductors connected together, the current will distribute among them based on their impedance. This can complicate the neutral load calculation and may require more detailed analysis. Let's talk about some common mistakes in neutral load calculations. Firstly, neglecting harmonic currents is a frequent error. Many electricians and engineers underestimate the impact of harmonic currents on neutral current. This can lead to undersized neutral conductors and overheating. Secondly, using simplified formulas without considering phase angles is another common mistake. Simplified formulas can provide a rough estimate of the neutral current, but they may not be accurate if the loads have significant reactive components. Thirdly, failing to account for single-phase loads connected to the high leg in a delta system is a significant oversight. These loads directly contribute to the neutral current and must be included in the calculation. To avoid these mistakes, here are some best practices for neutral load calculations. Firstly, always use appropriate measuring equipment to accurately measure phase currents and voltages. This will provide you with the data you need to perform accurate calculations. Secondly, use vector addition to calculate neutral current when dealing with reactive loads. This will ensure that you are accounting for the phase angles between the currents. Thirdly, consult the NEC and other relevant standards for guidance on neutral conductor sizing and load calculations. The NEC provides detailed requirements for neutral conductors and offers optional methods for calculating neutral load. Fourthly, consider using specialized software or tools for complex neutral load calculations. These tools can help you to account for harmonic currents, reactive loads, and other factors that can affect neutral current. In summary, while both three-phase 4-wire Y and delta systems require neutral load calculations, the specific approaches differ. Y systems primarily involve vector addition of unbalanced phase currents, while delta systems with a high leg require careful consideration of single-phase loads connected to the high leg. Always consider harmonic currents, voltage drop, and ground fault protection when designing and analyzing electrical systems. Accurately calculating the neutral load is critical for ensuring the safety and reliability of electrical systems. Remember to consult the NEC and use appropriate measuring equipment and calculation methods to avoid common mistakes.